Staying stable in a changing environment or dynamical stability is essential for everyday movement. I am Shandip De, a final year PhD student, and in the next 5 minutes, we will see how dynamical stability can become a biomarker for neurological disorders and can transform the healthcare. And surprisingly, it all starts with a small rocket. On the screen, you see two fingers pressing on force sensors to launch a rocket to a target height. When the total force Ft being produced by both the fingers equals the required force, the rocket moves to the green target. It looks simple, but this task lets us ask a key question. Can we quantify stability of the nervous system as a biomarker of neurological disorder? To turn the stability into a biomarker, we don't look at one trial. We look at the pattern across multiple trials. Now imagine repeating this task many times. Each dot is one trial. Index finger force on the x-axis, middle finger force on the y-axis. These points form a cloud along the diagonal UCM line. Combinations that keep the total force same. There isn't just one solution. There are many. And that flexibility helps the nervous system stay stable despite variability. But not all variability is equal. Variability along the UCM line does not affect the task. This is good variability. Variability perpendicular to it, odd line, changes the total force, and that is bad variability. When good variability dominates, the system forms a synergy that stabilizes the task. We quantify this balance as the synergy index, our biomarker of dynamical stability. We can measure this biomarker at different levels of the nervous system. Traditionally, we study synergies across fingers, but we can also look into a single muscle. A muscle contains many motor units, the smallest controllable unit, which can be grouped into functional clusters called motor unit modes. So now we have two levels, multi-finger synergies and intramuscle synergies. Measuring both may increase biomarker sensitivity. Prior work shows multi-finger synergies are sensitive to neurological disorders. Here the multi-finger synergy index is significantly reduced in Parkinson's disease versus the controls, suggesting a loss of dynamical stability across fingers and supporting it as a biomarker of neural deficit. The next question is, does this reflect only one level of control, or can intramuscle synergy reveal additional deficits? This is where prior work matters. Multi-finger and intramuscle synergies respond differently to the same challenges. Like dominance affects multi-finger synergies but not the intramuscle. Reflex-driven force changes are stabilized mainly by the intramuscle synergies, and fatigue tends to increase multi-finger but decrease the intramuscle synergies. Together, this suggests multi-finger synergies rely more on supraspinal control while intramuscle synergies rely more on spinal circuits. If so, measuring both could strengthen our biomarker by hinting not just that stability is impaired, but where the impairment originates. But all these were indirect clues, so we designed a direct test. We manipulated visual feedback. Participants produced force with feedback and without it. Since visual feedback is processed by supraspinal structures, our hypothesis was multi-finger synergies should drop without the feedback, whereas the intramuscle synergies should remain unchanged. And in a rare moment in science, our hypothesis actually worked. Multi-finger synergies disappeared and intramuscle synergies remained the same. This supports the idea of parallel stability systems, one supraspinal, one spinal, working simultaneously. In other words, using both synergies lets us probe stability at different neural levels. We then applied this idea to essential tremor patients. Although essential tremor is considered a supraspinal disorder, we found a significant reduction in intramuscular synergies. This was mainly due to the loss of flexibility of motor unit modes. So even here, spinal level stability is affected, and our biomarker was able to detect it and give us a new insight on the pathology of a known neurological disorder. So we started with a small rocket and a simple finger task, but what it revealed is a layered control system with parallel synergies at different neural levels. And by probing these levels, we can turn dynamical stability into a biomarker toolbox that detects neurological disorders earlier and more precisely. Because sometimes understanding how the nervous system launches a tiny rocket can help us understand how it begins to fail. Thank you.